The inverse function of the exponential function f(x) equals a to the power of x is the logarithmic function gx equals log base a of x. We are going to view the logarithmic function only as the inverse of the exponential function. The logarithmic function is the inverse of the exponential function. Inverse functions comes in pairs. If f is the inverse of g, then g is the inverse of f. In our case, we have g of x, which is log base a of x, and fx equals a to the power of x, being inverses of each other. The meaning is that the composition of the two functions is the identity function, because this is like doing something and then the exact opposite. If f and g are inverses of each other, then f of g of x is x, and also g of f of x is x, provided obviously that the x's are in the proper domains. When x is more than 0, f composed with g of x, which is f of g of x, is a to the power of g of x, which is a to the log base a of x, and this has to be x, and it is. And let's look at the other composition. G composed with f is g of f of x, so it's log base a of f of x, so it's log base a of a to the x, and it has to be x. The restriction in the first one is because the domain of the logarithmic function are only positive numbers. In the second composition, we don't have any restriction because the exponential function has a domain which is all real numbers. We can kind of summarize this that if you take x to be more than 0, then a to the power of log base a of x equals x, but x also equals log base a of a to the x. The graphs of functions that are inverses to each other are symmetric with respect to the line y equals x. If a function is assigning a value of some x to a value of some y, then the inverse function is assigning that y back to that x. As a result, to any point xy of the one-to-one function, there is a point yx on the graph of the inverse function. And the reason to recall all those facts are because now, if we know that this is the graph of y equals a to the power of x when a is more than 1, then we get that this graph is the graph of the logarithmic function with base a when a is greater than 1. You can observe the symmetry with respect to the line y equals x, and because 0 and 1 is a point in the graph of the exponential function, then 1, 0 has to be the other graph. And we know already that a to the 0 is 1, but now we also know that log base a of 1 equals 0. Let's talk a little bit about notation. If the base a is e, we call it ln of x, the natural logarithm. If a equals 10, we are not writing the number and we can write just log x. Log base a of a equals 1 and ln of a equals 1. Log base a of 1 is 0 and ln of 1 is also 0. In base 10, this is like log of 10 equals 1, and this is like log of 1 equals 0. Laws of logarithms. For all x, y positive numbers and a which is greater than 1 or a between 0 and 1, a to the power of log base a of x is x, and this is also equals log base a of a to the x. We are also going to write the parallel law using base e because this is the most useful base in calculus. So we also get that e to the ln of x equals x, which also equals ln of e to the x. Log base a of x to the n is n times log base a to the x, and the parallel in the natural logarithm is ln of x to the n is n times ln of x. Log base a of xy is log base ax plus log base ay. Ln of xy is ln of x plus ln of y. Log base a of x over y is the difference between log ax and log ay. With the natural base, it is the rule ln of x over y is ln of x minus ln of y. Be very careful. Log base a of x plus y or x minus y or ln of x plus y, ln of x minus y cannot be simplified further. Example, evaluate ln of log of 10 to the power of e to the power of 2. Let's go from the inside out. We are going to apply this law of logarithm to get that this is ln of e to the power of 2 times log of 10. But we know that log of 10 is log base 10 of 10, which is 1. Using that, this is like log base a of a is 1, and in this case a equals 10. We get this. Now we can use this law, that ln of e to the power of x is x. So ln of e to the power of 2 is just 2. And this is the answer. Example, I'm going to evaluate e to the ln of 3 minus ln of 7 twice. First time, I'm first applying rule of exponents, because e to the power of a minus b is e to the a over e to the power of b. In this case, a is ln of 3 and b is ln of 7. Now I can apply this, and I get that this is 3 over 7. Now I'm going to do it in a different way. First, I'm going to apply rule of logarithm. Ln of 3 minus ln of 7 is ln of 3 over 7. And e to the ln of 3 over 7, apply this property again, I get 3 over 7. Example, expresses the logarithm of one expression. We have here all those parts, and we need to combine them and to write them as ln of some expression. First thing that I need to do is to write as ln of something, which means I have to get rid of this 2 for the first one and 3 in the second one, and I have to write the 1 as ln of something. So let's start. The first thing that I'm going to use is that n times ln of x is ln of x to the power of n. And also, because I need to write 1 as ln of something, I know that 1 is ln of e. And I get that. Now I have to use these two properties, that ln of x times y is ln of x plus ln of y, and that ln of x over y is ln of x minus ln of y, to get the expression as written as 1 log. And I get that everything that has a plus is going to be on the top of this fraction, and everything that has a minus should be combined and being the denominator of this fraction. we have negative ln of z and negative ln of t to the power 4. It means that z and t to the power 4 should be under the fraction line. Example expresses the sum and the difference of logarithm. So now we're going to do exactly the opposite of what we did before. First, I'm going to apply rule of exponents to get rid of this power of 2. I just have to multiply each one of the roots or the exponents in the brackets by 2. And instead of 4 root of x, I get only square root of x. Instead of z to the power of 2, when I square it, I get z to the 4. And instead of y, I'm going to have now y to the power of 2. Now I'm using again those two properties. It means that everything that is in the numerator is going to be with a plus, and everything that is in the denominator is going to have a minus. And I get that. Please pay attention. In the denominator we have z to the 4 times y to the power of 2, and that's why those two has minus. Now I'm going to use that to simplify a little bit more, and I get this expression. Change of base formula. For all x positive number and a which is greater than 1, or a that is between 0 and 1, log base a of x is also log of base b of x over log of base b of a. If we are going to change the base to the ln base, to the natural logarithm base, base of e, then we will get that log base a of x equals ln of x over ln of a. Please note that because the change of base formula still have to make sense, when we take base a and we would like to express it using base b, then also base b has to be greater than 1 or greater than 0 and less than 1. The change of base formula is useful when we use calculators. Most calculators have only the natural base e and base of 10, but usually it's not very useful. But we will do an example. Let's express log base 5 of x plus log base 3 of x in the natural logarithm base. So we have to do two changes here. From the first one we get ln of x over ln of 5, and from the second we get ln of x over ln of 3. It means that what we get here is ln of x times 1 over ln of 5 plus 1 over ln of 3. The reason to write it like this, it looks to you probably a little silly, but it's not, because ln of x is a function, because x is a variable, but ln of 5 and ln of 3 are just numbers.